A particular commercial aeroplane cost $150 million new. The aeroplane will lose value at a continuous rate. This is modeled by the continuous decay function Ct, so C as a function of t, t being time, equals 150 e to the minus 0.053 t, where Ct is the value of the aeroplane in millions after t years. So let's just write that down. Ct equals 150 e to the minus 0.053 t. Okay. Part A. How much to the nearest $100 million would the aeroplane be worth precisely 5 years after being purchased? Part B. If the aeroplane is purchased in 2020, what would be the first year that it is worth less than half its original cost? So that would be less than $75 million. Part C. Find the value of B to 4 significant figures for a discrete decay model D as a function of t equals 150b to the power t, so that d of t is a suitable model to describe the same decay as c of t. So we're looking for a discrete model that does the same thing or very similar to the continuous model that we've just been given. So we'll start with part A because that's quite simple. So we just need the cost 5 years after purchase. So all we need is C of 5. So as is often the case, it's just a simple substitution. So it's 150 e to the minus 0.053 times 5, just like that. So if we go to our calculator, we just put it in 150. E is just above the ln button, you can see it there, e to the power of, I don't really need a bracket, but I'll probably put it in just to be safe. I always feel more comfortable with these if I've got it in, 0.053, forgotten the negative there, minus 0.053 times 5. Close the bracket, and that comes out at 115.0808925. We have been asked for this to the nearest $100 million, and we've been told that, we've been told that it cost $150 million new, and if you look at it, well, it starts with this 150. So imagine if t was 0, this function would give a value of 150. So I'm assuming that the units are $1 million anyway. In fact, it even tells me that. So the answer is 115 to the nearest whole number, 115 million US dollars. Okay, part B. So if the aeroplane is purchased in 2020, what would be the first year that it's worth less than half its original cost? So basically we need to find out when is 150 e to the minus 0.053 t, when is that less than 75? So there are different ways to do this. We'll use logs fairly soon, but right now the way I show it the most is to draw two graphs. So we're going to draw a graph of 150e to the minus 0.053, and we're going to draw a graph of 75. We're going to sketch, we're going to find an intersection. So menu graph, and get rid of any old formulas. So 150 e to the power of minus 0.053, and remember we don't have a t, we have an x. And then the second one is going to just be 75. So it's going to be a straight line, y equals 75. So execute and draw. and you can nearly see it, but you can't see it. So we need a sensible axis. So if you could potentially, it'd be nice to see what's going on with this. So if we know that this thing starts at 150, the maximum it can get to is 150, and it loses value. So if we go to our view window, if we just concentrate on the y's for a starter, let's say we go up to say 160, so we can definitely see 150. And then our minimum, well, yeah, we can probably go down to 0. I think that would be okay. And then for the x values, you're kind of guessing there. You know that it doesn't need to go into the negative, or it only needs to go just into the negative so you can actually see the y-axis. But then as far as the years, we don't actually know what that's going to be. So let's say we give it 15 years, and if we can't see the intersection, we'll just move it so it's more years. So then we'll draw it, and we'll have a look. And we can just about see the intersection there. So maybe I could have gone to 20. So let me just change that. Even though we can see it, might make it a bit clearer. So let's change x max to 20. And then you can see the intersection. I quite like it to be somewhere in the middle if possible, but it's only personal preference. So then we need a little sketch. So you've got the y-axis. You have the line 75, that's y equals 75. Then you have at the top, at 1 from 150, you have this function coming down kind of like that. And then you have an intersection here, which is what we're interested in. So we know that the y value is 75. What we don't know is the x value. So you go Shift, G solve, and we're looking for an intersection, and it tells you that x is 13.078. 13.078. So for the value to be less than $75 million, the time is going to have to be more than 13.078. So it's going to be year 14. Year 14, so t equals 14. So if we buy the thing in 2024, the answer is going to be, well, 2024 plus 14. So it's going to be year 2038. And that's the first time that this value will drop below $75 million. Part C. Find the value of b to 4 significant figures for a discrete decay model. dt equals 150b to the t, so that is the same, does the same thing. So we're looking to replace the sort of e bit with some b, or the e to a power bit with a b. So if I just write down the decay model we have 150 e to the minus 0.053 t, and we are looking for 150 b to the t. So really, if I can just mess around with this, I should be able to change to find an expression for this b. So let's see, if we just say 150 e, this is kind of like 150 e to the minus 0.053. And then if I just raise that to the power 3, if you just think about your basic index laws, the third one, this is a completely equivalent expression to this. So that must mean that this e to the minus 0.053 could be our b. So all I need to do then is go to the calculator and just work out, well, what is e to the minus 0.053? e to the power of minus 0.053 is 0. So b equals e to the minus 0.053 equals 0.94838 and so on. So we've been asked for this for 4 significant figures. So the 0 doesn't count, 1, 2, 3, 4. So it must be B equals 0.9484. So the discrete decay model dt must be 150 times 0.9484 to the power t. So that's our answer. Now I might just show you. Remember, this is a model. So when I say discrete model, what it means is this depreciation only happens once at the end of each year, as opposed to a continuous model where the value is gradually decreasing all the time. So seeing as we've got the calculator open, if we just go back to the functions, so menu, we'll go back into graph and go up. If we just sort of change function 2, we'll just put this decay model and have a look at it and compare some values. So 150 times 0.9484 to the power of x. So if we have a look at that, actually I'm not going to have a look at the graph, I'm going to have a look in table. So if we go menu and into table mode, which is number 7, you see that the functions are there anyway. If we just set the table up, let's have a look. So if we start with let's start with year 0, which should definitely be the same, and go up to, I don't know, 15 years, and just have a look at the numbers. I'm not going to write them down, but just for interest's sake, you can see that the values are quite similar. So this is the continuous growth model, Y1, so this is the value of the aeroplane at the end of each year, and this is the discrete growth model or decay model that we've just invented. So we compare year 7, you've got $103 million, or $103.5 million, and you've got $153.52 million. All the values are very, very close. So it looks like quite a good model. And one other thing we should say is that if you look at what this model does, well, what's the effect of multiplying a number by 0.9484? If you think about that, well, timesing a number by 0.9484, it finds 94.84% of number. And if you think about what that is, well, if you take that number away from 100, so if I just do 100 take away 94.84, so 100 take away 94.84, well, that gives me 5.16. So what this is doing, this is 5.16% loss each year. So that's what our discrete decay model does. It decreases the value of the aeroplane by 5.16% every single year, but it does it at the end of the year, and it doesn't do it continuously like the original model did.